In this lecture, we'll continue the parsing phase of a compiler.
Now that we're given a brief introduction to grammars, languages, and BNF, we can now explain how a parser works. So a parser receives as input the BNF description of a high-level language and a sequence of tokens recognized by the scanner. Now the fundamental rule of parsing follows. If, by repeated application of the rules of the grammar, a parser can convert the sequence of input tokens into the goal symbol, then that sequence of tokens is a syntactically valid statement of the language. If, however, it cannot convert the input tokens into the goal symbol, then it is not a syntactically valid statement of the language. We'll give an example of parsing the statement x equals y plus z. Now we're going to use a very simplified grammar. In fact, most realistic grammars would have hundreds, maybe even thousands of rules. Here, our grammar is just going to have 3 rules. The first one is that an assignment statement is defined as a variable then with an equal sign and then an expression. Now, expression is going to be a non-terminal that's defined as either a variable non-terminal or it is a variable plus another variable. So the plus sign is another symbol here. And then finally, the variable non-terminal will be defined as either the x terminal, the y terminal, or the z terminal. So x, y, and z are going to be our terminals in this case. So when we scan this expression, we'll get the tokens variable equals variable plus variable because x, y, and z are variables in this case. So variable would be the token, the resulting token. So then we can use rule 2 of our grammar to group tokens variable plus variable into an expression. So then we would get variable equals expression. So that means we can use rule 1 to group the tokens variable equals expression into the assignment statement non-terminal. And since this is our goal symbol, we would see that this statement is syntactically valid. Let's take a look at the parse tree for our statement and just convince ourselves that this does in fact work. So we do have x equals y plus z. So we would get our original tokens, variable equals variable plus variable. And then we would see that variable plus variable would become expression. And now we have variable equals expression, which sure enough would be our assignment statement. So once again, since we can construct a parse tree from this, this is a correct, a valid statement. Now, in our last example, we just picked the correct rules from the get-go and we were fine. But it's very common to have 2 or more rules that we can apply to the current input string. And it's the challenge of the parser to pick the correct rule, because if we don't pick the right one, then we may have an input statement that is technically correct, but the parser would say that no, this is not a valid statement. So how do we go about doing that? Well, we'll get to that in a little bit, but let me show you an example of what happens when you do not pick the correct rule for some statement. So in our last example, let's say we used rule 2 to parse variable from symbol y. So let's use that rule and convert it to an expression. So then we'll parse variable equals expression to our assignment statement. So instead of doing y plus z and make that the expression, we're going to make just y the expression. So let's see what happens when we do that. Let's take a look at the parse tree. So we still have x equals y plus z, and we still have x, y, and z being variables. But now the difference is that we're going to make just the y variable the expression. So we're no longer having y plus z be the expression. So sure enough, we do have variable equals expression. So we do have this assignment statement here. So we did get to the goal symbol, right? Well, this is still the wrong choice because it doesn't use all the tokens. We still have this plus sign and we still have this z that doesn't map to anywhere. We don't have assignment statement plus variable. That this doesn't work. So here what we found is that the parser has gone down the wrong path. So this particular choice was incorrect. If the parser does make an incorrect choice, then it needs to go back to that particular choice and then pick something else because it didn't work. It has to undo what it did, pick a different choice, and see what happens. So the parser is just going to keep doing this. It's going to keep picking until it either gets a correct parse or it's tried all possible parse options. And at that point, then it would just conclude that there's no combination that makes the parse work for that particular input statement. Now, parsing algorithms themselves don't just arbitrarily pick any rule. There is a process for picking these different rules. So what they do instead is they'll look ahead to see if that rule will work. So they pick a rule and they'll look ahead to see, does that look like it's going to work or not? And if so, they're going to continue down this path and try picking rules based on it. And if it doesn't work, they'll kind of say, okay, let's try a different option. And this is the idea of what are called look-ahead parsing algorithms. So they just look down the road a few tokens ahead to see what would happen if a certain choice was made. And this helps keep the parser moving in the right direction, and it does reduce the number of false starts or dead ends that we could get. So these algorithms can do very efficient parsing, even for large languages with hundreds of rules. For example, let's say we have the following input sequence, A, B, C. And we're not worried about exactly what A, B, and C do. We have A, B, and C. And let's say we have the following grammar. We have one rule that says the goal is defined as some term and then C, and a term is defined as either AB or BC. So this means we have two choices on how to parse the input string. We can either group the two characters A and B to form a term, or we could group B and C instead, and that would also form a term. Now, like I said earlier, a parser just doesn't do random choice. We can be a little bit more clever than that, because a random choice would cause us to be wrong about half the time. But if a parser is a little bit smarter and looks ahead, it can do a lot better. So we can clearly see that grouping B and C to produce the non-terminal term would cause some problems, because there is no rule that tells us what to do with the sequence A term. We don't have any definitions for that. So we would come to a very quick dead end if we tried to parse that approach. But instead, if we choose to group up A and B into term instead of B and C, that parser would quickly produce the correct parse tree. So let's take a look at this parse tree. So we would have A, B, and C. So we would group up A and B to get the non-terminal term. So now if we take a look at our rules again, goal is defined as term C, so we can group up term and C to give us our goal. So this sure enough does give us the correct parse.